Hi, and thank you for watching our presentation. My name is Big Pathanamon Tanunam. I'm a lecturer at the University of Melbourne, and today I will present our ICSE 2022 paper titled AutoTransform Automated Code Transformation to Support Modern Code Review Process. This paper is a collaboration with Gla and his PhD student from Monash University. In this paper, we present a new framework that uses a deep learning technique to automatically transform code to support code review process. And before we go into our framework, let's have a quick overview about the background and the problem. Code review is an activity that developers manually examine newly written code in order to improve its overall quality. And broadly speaking, the process starts with a code author makes a patch, which is a set of code changes, and submits it to the code review tool. Then the reviewer checks the source code and provides concern and feedback what to improve or revise. And usually the code author will revise the code to address the reviewer's concern. And once the reviewer agrees with the patch, it can then be merged into the code repository, for example, Git. Given a large number of patches and multiple rounds of reviews, code review can burden both code author and reviewers. For example, a prior study reported that it is challenging for them to switch context and keeping track of author reviews and tasks. Another study also found that one of the top challenges is receiving timely feedback. Thus, automated code transformation would be beneficial to them by automatically applying the common revisions during code review in the past to the newly written code, while allowing code authors and reviewers to focus on more complex part of the system. And with this goal, there is actually prior work has leveraged a neural machine translation approach to automatically transform code from the version before a review to the version that is approved or after version. And in particular, they leverage code abstraction and a recurrent neural network or RNN architecture to achieve these tasks. And broadly speaking, what they did is that they first abstract source code into reusable IDs, and they have a map between the IDs and identifier and literal of the code. And this approach seems to work well, especially for reducing the vocabulary size. However, the underlying limitation of this approach is that it cannot correctly transform code if a new identifier or literal is introduced in the after version. For example, in this after version, side panel has been newly introduced, so it has been assigned a new ID. And realistically, we cannot map this new ID into its actual value because the map is made based on the before version. Another limitation of the recent work also is the use of RNN architecture. Specifically, they use the RNN encoder-decoder architecture, which learn how the token sequence of the before version can be transformed into the after version. And moreover, they also leverage the feed-forward attention mechanism to capture the relationship between the consecutive tokens. Again, this architecture seems to work very well. However, a recent study has raised a concern that the current attention mechanism might have some difficulties in remembering long-term dependency between the tokens. Thus, the performance of the RNN architecture may be suboptimal when the sequence becomes longer. Based on these two limitations, we propose a new framework called AutoTransform, which leverages Byte-Pair Encoding and the state-of-the-art architecture called Transformer. And with BPE, we can address the limitation when a new identifier is introduced. So instead of using the IDs, BPE tokenized a code token, which is an identifier or literal, into the subwords based on the frequency of occurrence. Then from this subword, a new identifier can be constructed to a new identifier or literal. The use of architecture also helps us mitigate the limitation of the long-term dependencies. So generally speaking, rather than calculating attentions between the consecutive tokens, Transformer computes the attention for each token with all the tokens in the sequence. Thus, the model will better capture the contextual relationship between all tokens in the long sequence. And to evaluate our AutoTransform, we compare our approach with the prior work, and our experimental setup is as follows. First, we use the code review data from Android, Google, Ovid, which are open source projects that actively perform code reviews. And in this experiment, we aim to transform the source code at the method level. And to evaluate the effectiveness regarding the limitation 1, we classify changed method into two types, which are methods that have and do not have new token introduced in the after version. And we also classify the changed method into the small and medium size to evaluate the effectiveness when the sequence becomes longer. Therefore, in total, we conduct experiments with 12 datasets. And for each dataset, we use 90% for training, 10% for the validation and find the best model, and another 10% for the testing. And finally, we use the perfect prediction for our evaluation measure. And basically, we count how many methods that the generated code is exactly same as the actual after version. And here is the result for the small method in the Google dataset. And as you can see, considering both types of changes methods, our AutoTransform achieves perfect prediction about 4 times higher than the prior work. It is also worth noting that our AutoTransform can correctly transform the methods that have new token introduced in the after version, but the prior work cannot. For the method without new token in the after version, our AutoTransform also performs better than the prior work. And for the longer sequence, which is the medium-sized method, our AutoTransform also performs better than the prior work, even though we consider only the method without new tokens. And finally, the results are also similar for the other two projects. And these results suggest that our framework substantially improved the prior work for automated code transformation in the code review process. And since we use 2 new techniques to perform these tasks, which are BPE and Transformer, we are also interested to quantify the contribution of each technique. Therefore, we conduct additional experiments by using only one of the proposed techniques. And as the results, we will have 4 combinations between our framework and the prior work. Then we evaluate the accuracy of this approach. And here is the result for the Android dataset. And if you look at the first 2 columns, which are our AutoTransform and the one doesn't use BPE but only Transformer, and then you can see that the number of perfect prediction is largely different. And this result suggests that based on the same model architecture, BPE substantially contributes to the improvement. Regarding the different model architectures, we also can see that Transformer contributes to the improvement of our AutoTransform, especially for the medium method, which have a longer sequences. And finally, we observe the similar result for the other 2 projects. And these results suggest that both techniques used in our framework substantially contribute to the performance of the model. Okay, so here is the summary. Code review helps the team to improve the code quality, but it also can burden the developers. Thus, we propose a neural machine translation approach called AutoTransform, which uses BPE and Transformer to automatically transform the code from the version before a review to the version after the review. And our empirical evaluation with 3 open source projects show that our AutoTransform outperformed the prior work, and we also found that BPE and Transformer used in AutoTransform substantially help to improve the accuracy. And these results highlight that our AutoTransform substantially improved the prior work, and the result and insight from our work also contributes toward automated code transformation for the code review process. And here is just a highlight of our work. So you can check more details in our paper, and the preprint is available online. Thank you.